When you walk out into your backyard or you check on that indoor planted tank you've been working on and you spot yellowing, wilting leaves.
Oh, yeah. The immediate dread.
Right. The reaction is usually this very binary thing. You either assume total failure on your part, like, well, I killed another one.
Yep.
Or you assume it's just this inescapable biological inevitability, like it's time to go. So you basically write the organism off entirely.
Which is, it's a closed loop of thinking. It prevents any actual investigation into what's going wrong.
Exactly. But for an aquarist, someone managing multiple dynamic ecosystems, a dying plant isn't an ending. It is a data point.
Right. It's an indicator light flashing on a dashboard. Because we often treat botany or aquatic husbandry as this mystical art, right? Where things just spontaneously thrive or crash based on pure luck.
Like you either have green thumb or you don't.
Exactly. But when you treat an environment as a closed biological system, every single wilted leaf or like an unexpected algae bloom, it's a direct response to a chemical or environmental shift. You have to stop looking at the plant as a passive object and start viewing it as a reactive metric.
So true. Well, welcome to today's deep dive. Our mission for you in this conversation is to unpack a highly specific field note from an aquarist that demonstrates exactly that shift in perspective.
It's a really great example of it, too.
Yeah, we are pulling from a blog titled Notes on Fishkeeping. The entry is dated July 3, 2026, and it was written by an aquarist named Ang. And the central focus of the post is diagnosing the sudden, really rapid decline of a floating aquatic plant called salvinia-minima.
Often known as common salvinia.
Right, common salvinia. And this decline is happening across a series of outdoor ponds.
Okay, let's unpack this because I just have immediate admiration for the author's dedication here. We're talking about someone who is on, what was it, part 280 of a series?
Yeah, part 280. I mean, that shows we're dealing with someone deeply observant and totally committed to their craft.
Absolutely. And what makes this text so valuable is the methodology. Like you said, the sheer volume of entries tells us we are dealing with someone who relies on longitudinal data.
Meaning they've been watching this stuff for a long, long time.
Exactly. They have spent enough time observing these water features to really understand their baseline behavior, which is a critical requirement for spotting anomalies. The salvinia-minima is turning yellow and brown, and rather than just scooping it out and throwing it in the compost bin, Ang uses the failure to stress test their assumptions about aquatic biology.
Which is such a scientific approach. Because Ang starts this troubleshooting process by questioning the fundamental nature of the plant itself.
Right, before even looking at the water chemistry or the weather.
Yeah. Ang asks this very structural question. Do aquatic plants follow the same rigid life cycle patterns as terrestrial plants? Like, we know that many terrestrial plants are genetically programmed to just die off after a season.
Regardless of how perfect the environment is.
Right. So Ang dives into the literature for salvinia-minima and finds out that its lifespan is generally documented as just a few weeks or months.
Which is a huge clue. Or, well, it seems like one. And what's fascinating here is how tempting that baseline biological hypothesis is, especially when it gives you a convenient out.
Oh, for sure.
If the literature says the plant is genetically destined to die in a matter of weeks and your plant has been in the pond for a few weeks, the investigation naturally just wants to halt right there.
Yeah, it's like having a potted houseplant and saying, well, it's time to go. You don't look for a root cause. You just accept it.
Right. It is the path of least resistance. You can attribute the yellowing and wilting to a ticking genetic clock, and that absolves yourself of any environmental mismanagement.
But let's challenge that premise for a second, because is it really just old age, or is there an environmental trigger we're missing? I mean, salvinia-minima is a free-floating fern. Its entire evolutionary strategy is rapid vegetative reproduction.
Yeah, exactly.
Yeah. It fragments and multiplies to cover the surface of a water body as quickly as possible. And it does that to outcompete algae for light. So given that aggressive growth strategy, a short individual lifespan makes sense on a cellular level.
Sure, individual fronds will die off.
But a colony of it shouldn't just synchronously crash purely from old age, should it? Like, the continuous reproduction should mask the die-off of older fronds.
That is a crucial distinction. It really is. Because in a rapidly reproducing colony, the older individual plants might be reaching the end of their biological weeks-long lifespan, but the new offshoots should be vibrant and green, perpetuating the mat.
Right, the whole thing shouldn't just turn brown at once.
Exactly. A mass synchronized browning across the surface indicates a systemic failure, not just a genetic retirement. And Ang recognizes this nuance, which is great. The literature provides a plausible excuse, but the physical reality of the pond contradicts it.
The die-off is just too uniform within the affected area to be a natural generational turnover, which pushes Ang to reject the easy answer and move to the environmental variables. And I feel like the most glaring environmental variable for an outdoor pond in July is the macroclimate, the weather.
Oh, absolutely, especially July in an outdoor setup.
Yeah, Ang specifically notes that they are experiencing intense, scorching heat. And if you have a plant floating on the surface of the water, bearing the absolute brunt of direct summer sunlight, heat seems like the most logical culprit, right? For the leaves turning crisp and brown.
It's the loudest variable in the room. When troubleshooting any system, human nature gravitates toward the most aggressive stressor.
Like blaming a server crash on high traffic.
Exactly. If the server crashes during a massive spike in user traffic, you blame the traffic. If the salvinia wilts during a heat wave, you blame the sun. But Ang applies a strict process of elimination here by utilizing the layout of their setup.
Because they don't just have one pond.
Right, they have multiple. And the critical observation that flips this whole investigation is that the wilting is only occurring in selected outdoor ponds, not all of them.
Here's where it gets really interesting, because having multiple ponds acts as a built-in control group. It's like a detective story.
Oh, I like that comparison.
Yeah, like compare the heat to a prime suspect with a rock-solid alibi.
Yeah.
If the weather were the murderer, there would be victims in every single pond. The localized nature of the problem means the heat is innocent, or at least not the main culprit.
That's a great way to look at it, and it really highlights the value of having multiple observation points. Because if Ang only had one pond, they might have falsely blamed the scorching heat and stopped investigating entirely.
Oh, for sure. You just throw a shade cloth over it and call it a day.
Right. It emphasizes to you, the listener, the importance of comparing different data sets before jumping to conclusions.
But wait, let me push back on that logic for a moment. Heat doesn't act uniformly if the physical parameters of the ponds are different. Like, a shallow 50-gallon tub is going to heat up and evaporate much faster than a deep 500-gallon pond, even if they are in the exact same yard.
That's true. Water volume changes temperature stability entirely.
Right, so could the selected ponds just be smaller? Or maybe in a microclimate that gets less afternoon shade?
That is a highly valid point, and it's exactly the kind of variable isolation you have to run through in any system. However, in the context of Ang's setup and the rapid onset of the symptom, the macro variable of the heat wave is ruled out because the unaffected ponds share the same environmental exposure and basic parameters.
Okay, so they're similar enough that the heat should affect them equally.
Right. If we were dealing with different depths leading to massive temperature swings, the primary symptom wouldn't just be nutrient-starved yellowing leaves on a surface plant.
What would it be?
Well, you would likely see massive oxygen depletion, fish gasping at the surface, or even a complete crash of the nitrogen cycle due to beneficial bacteria die-off.
Ah, okay, that makes sense. So the heat might be an amplifying stressor, but the localized nature of the problem means it cannot be the root cause. If the sun was acting as a universal blowtorch on the yard, all the salvinia would be cooking. But we have healthy green colonies thriving in identical heat right next to the failing ones.
Which means we can definitively rule out the weather.
So Ang strips away the macroclimate, leaving a hidden variable. Something is fundamentally chemically different in the specific water columns of those failing ponds.
Which brings Ang to the final deduction, which is nutrient starvation.
Okay, let's get into this.
The salvinia-minima in the selected ponds is turning yellow and wilting because it lacks a continuous, adequate supply of nutrients. Specifically, it's lacking the bioload output from fish.
Wait, fish waste?
Yes. The failing ponds do not have enough or perhaps any fish producing waste to feed the floating plants. Without this waste, the salvinia starves, turns yellow or brown, and wilts.
Okay, I have to pause you there, because that conclusion requires us to examine the mechanics of an outdoor aquatic ecosystem.
Let's do it.
If this were a pristine indoor glass aquarium filled with reverse osmosis water, I completely understand why a lack of fish waste would mean zero nutrients.
Because there's nothing else in the water.
Right. But these are outdoor ponds. They're exposed to the elements. You have dead leaves blowing in, insects drowning, dust, yard runoff, bird droppings. There is constant organic matter entering that water.
A lot of organic matter, yes.
So why is the salvinia solely dependent on the continuous stream of fish waste to avoid starvation? Shouldn't it be able to feed off of everything else?
It comes down to bioavailability and the specific anatomy of salvinia-minima. You mentioned earlier that it is a floating fern.
Right.
It does not have true roots buried in a nutrient-rich soil substrate where heavy, slow-decaying organics break down. It has these modified fronds that dangle directly into the water column.
Oh, I see.
And for a floating plant with a hyperaggressive growth rate, it requires immediate, highly bioavailable nitrogen.
It needs the aquatic equivalent of an IV drip, not a heavy meal that takes months to digest.
That is the perfect analogy, yes. When a leaf falls into an outdoor pond, it has to undergo a lengthy mechanical and biological decomposition process before its nitrogen becomes accessible to a floating fern.
It basically has to rot first.
Exactly, it has to rot. Fish waste, however, bypasses that lengthy decay.
Because it's already processed.
Right. Fish excrete ammonia directly through their gills and solid waste. In a functioning pond ecosystem, beneficial bacteria immediately begin converting that ammonia into nitrates, and then into nitrates. And nitrates are the absolute gold standard fuel for salvinia.
So the fish are essentially biological processors.
They really are.
They're taking whatever they consume, insects, algae, prepared food, and rapidly converting it into a steady, continuous stream of pre-processed nitrogen that the salvinia can absorb instantly from the water column.
You've got it.
Without the fish acting as the engine of the nitrogen cycle, the slow decay of random outdoor detritus simply cannot keep up with the botanical demand of a fast-growing floating fern.
The continuous nature of it is what matters. A floating plant matrix can strip a water column of available nitrates in a matter of days.
Wow, days.
Days. If you remove the fish, or if the bioload of the fish is too small to support the sheer mass of the plants, the water becomes chemically sterile from the plant's perspective. It runs out of fuel, the chlorophyll breaks down, which causes the yellowing, and the colony starves.
So what does this all mean? I feel like we really need to step back and look at how this challenges our inherent bias against the concept of waste.
Oh, absolutely. It completely flips it.
Because in human systems, waste is a liability, right? It's the undesirable byproduct of a process that we spend billions of dollars trying to filter out, scrub away, or bury.
Yep.
We equate clean with healthy.
We do.
But in the context of Ang's ponds, chemical sterility is a death sentence. The waste is actually the essential lifeblood keeping these plants alive. It's the load-bearing pillar of the entire ecosystem.
If we connect this to the bigger picture, Ang's field notes demonstrate a perfect visualization of closed-loop systems biology.
Closed loop, meaning nothing is truly wasted.
Exactly. In ecology, the concept of waste literally does not exist. The output of one biological process is the required input for the next. The salvinia-minima is not just a decorative element floating on the water.
Right, it's not just there to look pretty.
No, it is a vital, active gear in the pond's nitrogen cycle. It is actively pulling toxic nitrates out of the water, effectively purifying the environment for the fish, while relying entirely on the fish to provide those nitrates.
They are locked in this, symbiotic dependency, which means Ang's initial observation of the dying plant isn't actually a botanical problem at all.
Not at all.
It is a system load problem. The yellowing leaves are essentially a dashboard warning light indicating a break in the supply chain. If the plants are starving, it means the biological engine of the pond, the fish bioload, is either missing, insufficient, or perhaps being overly aggressively mechanically filtered before the plants can access it.
That is the ultimate takeaway from this troubleshooting exercise. You cannot look at the failing component in isolation. Ang didn't just ask, what is wrong with my plant? They asked, what is changing in the inputs of this specific environment that is causing this component to fail?
It forces a systems-level analysis. You have to trace the missing input upstream.
Always. You always have to trace it upstream.
It's a phenomenal reminder for anyone managing complex systems, whether you are maintaining an aquaponics setup, debugging a software architecture, or, optimizing a supply chain. When a localized failure occurs, your instinct will be to blame the most obvious, overarching stressor, the equivalent of the scorching heat.
You'll want to blame the macroeconomy, or a sudden spike in demand, or just bad luck.
Right, but you have to demand control data. You have to look at the adjacent ponds, look for the discrepancies in the data.
You have to find the boundaries of the failure. Where is the system still functioning correctly under the exact same macro stressors?
And once you isolate the difference between the failing pond and the thriving pond, the hidden variable almost always reveals itself to be a missing localized input.
9 times out of 10.
We started this deep dive with a seemingly mundane image, right? Just a yellow wilting leaf on a pond weed. And by following the structured deduction of a dedicated aquarist, we dismantled the assumption of genetic inevitability, we used spatial discrepancies to rule out intense weather, and we finally uncovered a broken nutrient supply chain hidden in the chemistry of the aquatic nitrogen cycle.
It's quite a journey from a single wilted leaf.
It really is.
This raises an important question, though, and it is something for you to consider as you look at the ecosystems you manage in your own life, whether that is a literal garden, a team at work, or even the operational processes in your home.
Oh, I like where this is going.
If the complete decline of the salvinia-minima was caused by the lack of a byproduct we instinctively view as dirty and disposable fish waste, what hidden dependencies exist in your own systems?
That's a great point. What are we filtering out?
Exactly. What informal process, seemingly redundant communication, or casual waste output is actually the critical invisible nutrient keeping another part of your ecosystem alive? What happens to the balance of any system when a single output is suddenly removed?
It fundamentally changes how you evaluate the things you try to filter out or optimize away. The next time you see a failure in your environment, don't just accept it as inevitable and don't immediately blame the sun. Look for the missing inputs. The answer is usually hiding in the water.